Of course, we could go on from here and compute F7, U7, S7, F8, U8, S8, and so on. And the listener will have realized that the probabilities Fn and Un will actually coincide all the way up till trial number 9. And that is because through the first 9 trials, it is only possible to have a single success run of length 5 at most. One can't have 2 success runs of length 5 in the first 9 trials. So the first place where F and U start to differ, start to diverge, is at trial 10. Of course, the Sn probabilities are more complex. They have to take into account not only a success run at a given point, but also possibly previous success runs. Doing it by hand and working our way forward does not seem to appeal. This is looking to become algebraically cumbrous. And so it would be wise for us to step back and take a look at the larger picture. See what we can deduce about the problem. And of course, a key principle is immediately suggested, that of additivity, partitioning the problem into a proper piece. So let's start by deconstructing the occurrence of success runs again. Suppose we are looking at trial n, and we are asking, what is the chance, Sn, that there is a success run of length 5 at or before the nth trial? A key principle immediately suggests itself, and that is the following. If there is a success run at or before the nth trial, then manifestly there must be a first success run somewhere earlier in the sequence. This is a necessary and sufficient condition for there to be a success run at or before the nth trial. And that immediately suggests to us a partition for the problem. Recall, the event at hand of interest to us is the event Sn, that there is a success run of length 5 at or before the nth trial. Well, for this to happen, there was either a first success run at trial 1, or a first success run at trial 2, or at trial 3, 4, 5, and so forth, or a first success run at trial n. In other words, S sub n is the union of F1, F2, F3 through Fn. Now, the student will have realized that I'm belaboring what appears to be a simple point, but this is key. There also appears to be a certain amount of redundancy here, because F1 is empty, F2 is an empty set, so is F3, so is F4. One cannot have a success run occurring at or before the first, second, third, or fourth trials. But it is unwise to unnecessarily complicate our notation. We may as well start with the first trial, keeping in mind eventually that the probabilities for the first 4 trials are going to vanish quietly like the snows of yesteryear. Right. So let's say then we have a partition. Sn is a union of n disjoint events F1, F2 through Fn. Of course, the principle of additivity promptly rides to the rescue. The probability of Sn then must be the sum of the attendant probabilities of F1, F2 through Fn, or in our compact notation, Sn must be equal to F1 plus F2 plus F3 through Fn. We spent a fair amount of time on what in retrospect will appear fairly simple. But the idea of linking a success run somewhere in a sequence to first success runs is not immediately obvious. And it is this key idea that allows us to open up the problem. And therefore it is worth spending time on it, relishing it, understanding it. What we've got here is a slogan. We are interested in the probability Sn. And what our additivity principle tells us, what our partition tells us is, if we know the first success run probabilities, F1, F2, F3, and so on, then we can deduce the probabilities Sn of a success run somewhere at or before that point. This is our first slogan, and this is, of course, a political age, so we're going to build it in a sequence of slogans. And eventually we'll get to where we want to get to. But this is a good starting point. We have decomposed a problem into bite-sized pieces. Our questions now are, well, what can we say about the Fs? This comes up next.